What's good, everyone? Welcome back to another video. Today we'll be doing another LeetCode problem, and for this one, it's just basic. It's just on basic binary trees. So, once again, I'm gonna read the prompt, explain a little bit, write out the code, explain the code, finishing off with time and space complexity. Okay, so LeetCode problem 104, maximum depth of binary tree. Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. So, we have example 1, 327, 32015. That seems like the longest, obviously, just by looking at a picture. And what we're doing is we're just running the code to find out what's the maximum depth of the binary tree, right? Yeah, since this question is just binary tree in general, we can use both BFS and DFS. And this question itself is also like pretty sure when you filter it, it'll show the DFS works, BFS works. Like, you know, when you search them up, this question has like, you can use both. I mean, you get the idea. It doesn't matter. So for this question, I'm going to be showing both ways, both solutions, the DFS method and the BFS. Okay. So, all right. So let's first understand that this question is saying that the maximum depth is basically number of nodes along the longest path from the root down to a leaf. And oh yeah, by the way, I'm doing DFS first. So if I want to do DFS, I gotta first think of this question recursively. If tree is empty, then that means the root is equal to null, and that also means that the depth is 0. Now, other than that, what I want to do is going to be 1 plus the max depth of left and max depth of right. Now, so why? The longest path must go either into the left subtree or the right subtree. And whichever side is deeper, we take that depth and add 1. The reason for that 1 is because it's for the current root node. I'll show you through the example if you don't understand. So this is basically what we're doing for DFS. So let's write out the code first. First, I want to do the base case. And like I mentioned, this base case is basically going to be the empty tree has depth of 0. So if root is equal to null, return 0. That's it. Because if tree is empty, there's no depth. Okay, so now we want to do the recursively find depth of left and right subtrees. Integer left depth, and it's going to call itself right here. Call the function itself the max depth. We're going to have the root dot left. Integer right depth is going to be we're going to again call itself the root of right. And then we want to return 1 plus the math dot max of left depth, right depth. And that's it. Nothing else. So we run the solution. While it's running, oh, never mind. It's already done. Perfect. Okay, so let's just submit it real quick as well. Yay. Okay, cool. All right, so first things first. This part, LeetCode calls this function with the root of the tree. We return an integer representing the max depth, which is number of nodes on the longest root to leaf path. This part, base case of the recursion. If the subtree is empty, then the depth is 0. Right here, this part right here is going to show, this is where we recursively compute the maximum depth of the left subtree and right subtree. These calls go down until they hit null leaves, and then it's going to unwind back with depth. So obviously, and then for this part, it's basically for the current node, its depth is equal to 1 for the current node itself, and then it's going to plus the larger of the two subtree depth. So if I want to implement what I basically implemented for that part would just look something like this. 1 plus max of like that. Root dot, there we go. And then like that. See it? Okay, cool. So let me just make a quick walkthrough. So first things first, we want to first call the max depth of 3. Oops, 3. There we go. Max depth of 3 because that's the root. Now we're going to look at the left depth. Left depth is going to be the max depth for the left of 3. So 3 root left is 9. And then the right depth is going to be max depth of 20 because that's on the right. And then return 1 plus the max of left depth, right depth. There we go. First things first, we want to look at this part. Oops, this part, which is the left side. So max depth of 9. Left depth. So for 9, we want to look at the left. That's null. So max depth of null is going to be basically 0. And then the right depth, max depth of the right is also going to be null. So that's also 0. So now we return 1 plus max 0, 0, which is going to be 1 plus 0, which is 1. So now we're done with the maximum depth of 9. So this part is done. And we get that we get the math for this part for here, which would be 1, and then this part is gone. So now we remove this part. Now we do the second part of max depth 3, which is max depth 20. So max depth 20. Oops, there we go. Now for that part, again, same thing. Left depth is going to equal to max depth. What's the 20 left? 20 left is 15. And then right depth is going to be left depth of 7 because that's on the right side. And then we want to return 1 plus the max of left and right. So for the 20 part, let's look at max depth 15. So max depth 15. I'm not going to write the whole thing out. So left is going to be null, which is 0. Right is going to be null, which is also 0. So we want to return 1 plus max of 0 and 0, which is going to be 1 plus 0, which is 1. So this part is 1. Now we look at 7. Max depth of 7, left side, null, so 0. Right side of 7, also null, so 0. So it's going to return the same thing, 1 plus the max of 0, 0, which is 1 plus 0, and that's 1. So we finish the right side with 1. Remove this part. And then now we're done with this, and we're done with this. So now we do 1 plus the max of 1 or 1, which is 1. So it's going to show 1 plus 1, which is 2. So now we got the right side, the right depth, which is 2. And we're done. We're done with that one too. Now, we finally reached the very end of the max depth of 3, which is going to show return 1 plus the larger number is 2, so it's going to be that. And then it's going to produce 3. So once that's done, what it's going to return will be this part, which is 3. And the output is 3, you know. Did I run this? I think I run it, right? Did I submit it? I think I submitted to. Probably. Okay, so that's basically for DFS and DFS. Now what we're gonna do is I'm gonna be showing you the BFS version. Okay. Okay, and by the way, for the BFS version, we're gonna be doing the idea of it is we're gonna use a queue and do the level order traversal. And so each level that I traverse, we're going to add 1 to the depth. So like I mentioned, DFS, it goes all the way down to the lowest part. Whereas BFS, we're counting each level, every node. Okay? Before going down. So for BFS, what we wanted to do is we're going to import a linked list. And then import Java queue what we have here is we're going to first do the base case, which is if root is equal to null, then just return 0. Now what we're going to do is we're going to have q tree node, which is going to be q equals new linked list. Afterward, we're going to have q dot offer the root. And then also don't forget we're gonna have the depth because that's what we're counting. So while the queue is not empty, so now we're gonna have a level size, which is gonna show the queue size. This is just basically the this part right here is basically number of nodes at this level. And that's going to be helping us with the for loop. So I'm going to have the int I equals 0, I less than the level size, I plus plus. So with this thing, it's going to tell us, hey, how many nodes are in this level? And let's say we have a 9 and 20, so the size is going to be 2, right? Inside the for loop, we want to go through each of the node. And once the for loop is done, we basically finished that level. So we're going to have tree node, and we're just going to call it node. And we're going to have q.pull. If the node.left is not null, then we want to do q.offer node.left. And same thing with the right side. If that's not equal to null, q.offer.node.right. Once we finish all of that, boom, boom, we exit the for loop, and then we're going to do that plus plus. So keep in mind, that doesn't mean we're done. This part just means we're done with one level. We're like, after finishing this level, increase depth. And then once you're done with the whole while loop, then you can return the actual depth. And that should be it. A little bit longer to write, but not that bad. It is still very easy to understand. There we go. Let me quickly explain it real quick. So for this part, we basically start with depth 0. And then while the queue isn't empty, we look at how many nodes are currently in the queue, right? And that's basically the level size that I talked about. And then push their children. Or basically, no, sorry. We don't want to push their children yet, sorry. We look at how many nodes are currently in the queue, which is the level size, and that's one level. Afterward, we want to pop exactly the level size nodes, which is one full level, and then push their children. After that, after processing that level, then we increase the depth. Once we process all the levels, the depth will show like the maximum. Ooh. Okay, so let me do a very, very quick example. Once again, we're going to be doing with example 1. So what it's going to do here is we're going to first have the initial, which means we want to queue the 3 first. So we have 3 in here, that being 0. So this part will be the loop, the first loop. Level size, we want to look at the level size, and that's basically the queue size. Queue size being 1, because there's only one node at 3. So yeah, when that's done, we want to pop it. Then we want to have node equals 3. So once node becomes 3, the queue is now empty. Let's look at the node.left, which is 9. So enqueue that. Enqueue the 9. Afterward, node.right is not null, but 20. So we want to enqueue that as well. There we go. So 20. And now we basically finish the level. End of this level. So now we want to increase the depth by 1. And now we are done with this part. So remove the 20, remove the 9. and then remove node equals 3. Now the size is gone, and yeah, that's it. Now we are on loop 2, where we have q in is the 9 and 20. So now the level size becomes 2, and we want to do 9 first. So 9, when the 9 becomes the node, then the q removes the 9. We basically pop it. Now we're gonna look at node.left for 9. So it's null because it's null. That means there's nothing to q. Now we look at the node.right, which is also null because there's nothing on the left for 9, nothing right for 9 as well. So now when that's done, we still have 20. Now we're gonna basically change it into 20. So it's gonna dequeue the 20. Node's gonna be 20, and then we look at the node left for 20 and node right for 20, which is 15. So we're gonna add the 15 in, and 7. So we're gonna add the 7 into the queue, or in queue it basically. Sorry, not add, but it's better to just say in queue since we are talking about queues. So like that. Okay. So now the level ends, and now the depth becomes 2, because remember, once we finish the for loop, we want to increase the depth. But we're not done with the while loop yet, so we can't return immediately. Now we do a third loop. So loop number 3. This time we are looking at, again, the queue size is 2, because there's 2 nodes inside. And I mean, there's two values, whatever you want to call it, inside the queue. So again, the size is 2. We want to first pop the 15, and that 15 is going to be the node. We look at the node.left, which is null. So it's not, so we just skip it. Node.right for 15 is also null. So that's done. Now we want to add the 7 and look at 7 left and right. Both again are null. So 7 is done. And now once we finished, we want to increase the depth, which becomes 3. And now because the queue is empty now, this while statement is no longer true. So now we return the depth, which will be 3. So we just basically return depth 3. And that's it. That will be basically now that the queue is empty, we're going to exit the while loop, and return that depth equals 3. So this way we process all 3 of the levels, so the maximum depth is 3. What was it? Did I already submit it? Yeah, I think I already did, right? Yeah, okay. All right, so just let's wrap it up and just, because the video has gone long enough. From a DFS view, it's going to be it works from top down, right, with recursion. While for BFS, we count how many times we process a level in the queue. So now we're going to be doing a quick time versus time and space complexity for both of them, right? God, I'm coughing a lot more, which is not good, but it's fine. Okay, so let's do the time versus space. This will also answer, like, if you have a question like, hey, which one's better? Is DFS better or BFS better? Then it'll answer it, which, by the way, they're actually the same. Both of them are big O of n. So complexity for both will be time is big O of n, space will also be big O of n. And let's talk about space. For space, the DFS is recursion. So, and then for the BFS, it's Q. So they both are big O of n in the worst case. Because like it's sort of like, if it just depends on, there is no like this one's correct and that one's wrong. It's more like if you want to do recursion and DFS thinking, then obviously show DFS, right? But if you want to do if you want to do it like as in like a levels and BFS with a Q, then show BFS. It's really up to you. They both work exactly the same because for the space, right? The DFS recursion is big O of H. Wait, not big H, small h. Because this part is call stack. And then for the worst case, H is going to be equal to N, right? N being, by the way, N equals the number of nodes. And, oh, yeah, by the way, just in case you want to know, H is the height or max depth. Damn, why am I coughing so much today? Okay, so there's that. And then for BFS, oh yeah, this part is DFS, by the way. DFS. For BFS, we are looking at big O of, we can call it W. W being the width of the tree. So we can call this height of tree, width of tree. So you can kind of see DFS talks about the height, BFS talks about the width. And again, like I said, both case on the worst case scenario is big O of N. And the best case scenario would be log of N if it's balanced. And then for the time, big O of N, because we visit each node exactly once. And that is it. Yeah. Oh, missing a C. Well, actually, it doesn't even matter. You get the idea. And then I accidentally forgot this, so let's just double check if it runs. Yay. Okay, cool. All right, and yeah, that's basically it for the video. Thanks for watching. I showed both versions. Hopefully it makes sense. If it doesn't, just leave a comment, ask me the question, and I'll try my best to respond or reply it. Thanks for watching.